So in the chapter of footings, that's part 11, a quick introduction of footings. Footings are those members that transfer the load from our columns down to the soil, to the foundation. Why we need these footings is because soil is much weaker than our members, our structural members. So when you go down with that point load, you will shear off the soil. So you need to have a bigger kind of member that distributes and gets some stress down to the soil, and that stress should be within the limits of our bearing capacity, within the capacity that the soil can take. And so what this does is actually exactly as your foot. You know, what your foot is doing is it distributes the load that comes on your leg from your body down to a bigger area. And as we know, P over the area gives the stress. So the bigger the area, the smaller the stress will be, right? And if you have a smaller stress, you will safely take that load of the building down to the soil and to the ground. So that's exactly what our footings, the purpose of the footing is. Now the types of footings, we have spread footings. Those are isolated ones like those guys. And we have combined footings, like this guy here, that combines more than a column. We have a strip footing that is applicable to the walls or line loads generally. We have a pile cap if we have deep foundation, like the piles that goes all the way. This is how it looks like. It's exactly like a footing, but instead of resting on the ground, on the soil, it's resting on several piles that take the load down to a stronger soil, deeper than the surface. And then we have the raft or the mat foundation. This is like this one. Very, very commonly used type of foundation for high buildings. And for buildings that generally gets a lot of spread footings that constitute maybe more than 2/3 of the area, then it's easier and less workmanship to just make one raft foundation underneath the whole building. How we size the footing is generally using our allowable stress design method, which means we take that load, P, to be pretty much the dead plus the life, or any unfactored load considered with us. And then we size the footing. Our footing is sized, B times L. So that area is sized based on P from the service loads. So the P divided by the allowable stress, right, we'll call it bearing capacity, will be equal to the area. Then we will go into the details of what P exactly is and how we bring it to be able to estimate our A, which is pretty much our B times L. And then we use the LRFD in the design of the member itself, just like flexural and shear and punching shear, as we will see later on. Talking about the soil pressure, and the load on the column is transmitted vertically to the footing, which in turn is supported by the upward pressure. Exactly as you say, for every action, you have a reaction. And what we assume in our design is the linear or average stress distribution of the stress underneath the footing. In reality, do you think it will exactly look like a straight line underneath? The answer is no. It depends on the type of the soil. They found that for actual stress distribution for granular soil, like gravel and sand, it will look like this. It will have higher stresses in the middle and then lower at the sides. And they found that for clay, maybe in silt, cohesive soil that counts on cohesion, it will look more like this. In fact, a lot, or I would say 90% of the soils that we deal with in our daily life is a combination of different types of soils. You'll have sand and a little bit of silt, a little bit of clay. As you go geographically in different places, you'll have a combination. So as designers, what we end up doing is we just assume a straight line relationship. And any differences will be taken out within our safety factor assumptions. Now let's think about any footing is subjected to an axial load and moment. In case you have moment applied to the footing, I want you to think about yourself leaning forward. Think about this person. you see if I started to lean forward, right, is as if I'm putting some moment on myself. You agree? And in this case, your P goes a little bit higher or away from the original P with an eccentricity. So we can simply say that the moment is equal to a P times E, just like the way we talked about this relationship in the column design. The same way, if you have a footing that has moment, if the moment goes very, very high, this can end up turning the footing, right? This can end up making the footing leave the ground. But in fact, this soil is not like very hard soil, so it will start uplifting on some areas and stay in contact in other areas. How do we get this relationship? Using this nice equation that we studied before in solid mechanics and strength of materials, P over A plus or minus my over I, right? So this relationship will tell you that using this P and this M, I have a P and M, right? I will get extra stress here. This stress will be the plus stress. You see this plus sign? And that stress here will be the minus stress, right? Until one point, you have P over A equals my over I, and in this case, that part will have a stress equals to 0. So reaching the 0 stress is not a favorable solution, because beyond this, you will uplift the soil, uplift the footing, which is not a good design. So came this guy called Kern, and he decided to find this distance for us. So he found this distance, and he said that if your P is within the middle third of your footing, if your P is within this area, you will ensure that you are always in contact with the soil. Exactly at the edge of the middle third, you will have a 0 stress on one side and double the average stress on the other side. So in this case, if I delete this guy, this case exactly will get us like this. That's what Kern talked about. So you have 0 and you have double the average stress, the highest stress. Now if you go further than this, if I go like here, it means you will end up doing this, which is not favorable because this part is uplifted already. Okay? Now what is the current distance? Since we said it's the middle 1/3, so that means this here is L over 3. So your eccentricity is actually L over 6 because it's half of this. So the current distance is L over 6. If you're within the 1/3, that means your eccentricity is less than L over 6 and you are not uplifting. You go beyond this, you will uplift. So I will convert my moment to be in terms of P. Again, moment equals P times E. So I calculate my E equals M divided by P, and I make sure that the E is less than or equal L over 6. If it's less than or equal L over 6, then you did not uplift and you are all compression. It goes beyond L over 6. That means part of it is uplifted and not in contact with the soil. Let's look at the stages of this. Here are the stages. I have the P exactly in the middle, uniform distribution, where it is 0 moment, so I have Q equals P over A. Now I start moving a little bit to the side, but I'm still within the current distance. I'm still in the middle 1/3. I have higher stress on one side than the other side. How much is this? It will be P over A plus My over I. And this one will be P over A minus My over I. Simple. And then I push it forward until I reach exactly E Kern. I will get exactly 0 stress on one side and exactly double this average stress on the other side. Why? Because this area needs to be equal to this area. And then I go beyond this, it will be redistributed. And then I have an area that is uplifted with no compression stress. Unfavorable design, and no one would accept it. What's the bearing capacity? The bearing capacity is the load, geotechnical speaking now, is the load or the stress at which my soil will exhibit what? Shear failure. Have you seen this before? Probably in geotechnical engineering. You put so much load here, this guy goes out, this guy goes out, this one will pop up like this, and then you end up with shear failure. The load, shear failure of what? Of soil. The load that causes stress to do this, that stress is called the ultimate bearing capacity. So the ultimate bearing capacity is, theoretically speaking, is the stress that the soil will fail in shear at. Then what is the allowable bearing capacity? Now, as engineers, and we said we talk about allowable stress design method, right? Allowable stress design method. So what happens if I tell you, for example, the bearing capacity, this is the ultimate now, is 600 kilonewton per meter squared. Okay? That means when I reach the load that makes the stress equal 600, I will fail the soil, definitely. I say, okay, give me a factor of safety equals 3. Then I design for a bearing capacity, this is allowable now, equals 200 kilonewton per meter squared. Clear? What happened here as a designer, because I'm using service load with the allowable stress design methodology, then I have to lower down my capacity so much to be able to take the load and safely say I've designed I sized my footings to not reach the bearing capacity. So as a designer, if I get 205, 220, it's unsafe, even though my ultimate bearing capacity is still far. But for design purposes, I have to be as far as possible. Let's now think about those three components. The first component will be our load coming from the column down on the footing. Tamam? If that footing is supporting a building structure, and that load is in the red color. You know, for every action we have a reaction, so the reaction comes down as red color. Everybody agrees? So I'll put this here as the red color underneath the footing. Imagine that I also have the footing weight itself. So I have the footing weight here, will be in blue color. Here's the footing weight, right? And then the footing weight goes down, then there is a reaction from underneath as well, and I will also put it in blue, right? And we also know that the footing is underground, but there is some overburden. So the overburden is the green color arrows. Those are the loads coming from soil above the footing, from basement loads or from ground loads and people walking on the ground that is exactly on the footing, right? And that will have what? Some reaction down underneath. So now I have three colors of three reactions for three different sources of loads, right? Everybody understands how things are working here, right? Now, the question will come once we look at the limit states of the footings. Let's now go over the limit states. Now, what are the limit states? Limit states are those failures, if you want to think about it this way, or ways of failures that we are trying to prevent when we go as designers to perform our design. So the first one is, very simply, your soil failure limit state, right? What's the soil failure limit state? Very simply saying that your bearing capacity goes higher than what you have, your stress goes higher than the bearing capacity, and you sheared off the soil. So this is shear failure in the soil. And then the way to prevent this is to have, remember, stress equals P over A, right? Is to have stress that is smaller than our Q bearing capacity, right? And to do this, you can simply say that I will increase my area, right? So increase B or L or both. Very simple. This is the very first limit state, that you would like to have your area of the footing big enough to have a stress less than your bearing capacity of the soil. Let's go to the second limit state. Is think about this footing as a double cantilever. If I have a double cantilever, I would think like this one, my footing, I'll make it a little bit exaggerated. Think about it doing this, right? Because you have a stress down here that pushes up. Agree? So that stress pushing up, I will say that since it's a cantilever, I'm breaking this guy out. I'm breaking this guy in flexural, right? Once it breaks in flexural, this is a flexural failure, bending, and your tension is at the bottom of the footing. So this is called the flexural limit state, flexural failure. Okay? Now, how can we prevent this? You see this moment here that is caused by that area, the load from this area. That moment needs to be what? So my MU needs to be less than phi mn of the footing itself. Simple. How can I do this? I can increase phi mn. How can I increase phi mn? By increasing either D or increasing AS or increasing B and L, because this is B, right? This is, in my design, it would be considered like B. So just any means to increase your moment capacity of the footing itself. The third way to fail is the shear failure. Since we said shear, the moment, then we have to also talk about shear. And then in this case, we will talk about the one-way shear. One-way shear, because in footings, there's also something called the two-way shear. How does that happen? I simply have a footing that looks like this, and here's my column, right? Think about this shearing off and splitting. So this guy gets out. If this guy is splitted out here due to the big load here, right? As if this whole load is here, right? But think about this being very weak in shear, and it shears off a whole side. That's one side shear that was taken off, right? So this here is taken off by this force. F here pulls this guy out, right? Now, that means I have a VU, a shear, that needs to be less than phi Vn. Okay? How can I prevent this? Very simply, increase my phi Vn. And to increase the phi Vn, I can either increase B or D or material properties F prime C. Here also we have F prime C, right? Or we can provide shear reinforcement. That's a solution that is not very liked in footings, but in some cases we end up doing, especially like in bridges or so. The next limit state is the two-way shear. What is two-way shear? Punching shear. So we have something called the punching shear failure. What do you mean by this? It means that I have a very heavy load. This is also called two-way shear, right? If I have my footing looks like this, think about this shearing by penetrating the whole thing. So this whole thing goes down. The footing itself goes up, and the column goes down. So the punching here goes also with some forces here on the side. So you end up with a VU that is also smaller than phi Vn for shear. And in this case, we can also increase phi Vn by increasing the B, and the D, and F prime C. The last one is, which is number 5, is the connection between column and footing. And that connection is due to the fact that both, one will have its dowel reinforcement. The reinforcement here coming from down here is different than the one up here. and two different F prime C's and bearing of column on footing. So there might be something that happens here. And what you need to make sure that is your P ultimate is less than your P bearing at the connection, right? So those are 5 limit states. Now, if we go to the 5 limit states and try to compare them to the arrows that we looked at here with the combination of colors we looked at, we need to ask this important question. Which colors apply to which limit state? So to answer this question, I have to differentiate between two types of pressures. The first pressure I have is the gross pressure, gross soil pressure. Where does it come from? It comes from all the loads on top of the soil. All the loads that causes this pressure, which means all 3 of them. I'm going to make it in black. All 3 of them are the gross. Now, if I look which one will cancel each other at the footing outside the column, I will see that those guys will cancel those guys will cancel those in terms of finding straining actions on the footing itself. So to find the shear and the moment on the footing sections, I will only consider the red one, and the red one is the net. So I have gross pressure, which is all the pressures together, accumulating all the loads on top of it, including the soil, including the life load on the ground or basement, and including the footing weight. And then if I just separate those, I take only the load coming from the column itself. This will be the red one. What is the red one? It is the column load that causes the net pressure. This is the extra load that I added, in fact, to cause this moment and this shear, right? So those guys come from the net. So if I relate this to the limit state, I will simply say that all of them here will be affecting limit state 1, which means gross. So what causes limit state 1 is gross pressure. All of them together. Now what causes case 2, 3, and 4, and 5 will be the net. So the reason here, all of these guys will come from the net pressure. Okay? So when I'm designing, at the time I'm looking at sizing the column, sizing the footing, I only have the column load. I have to add up footing load and loads coming at basement to be able to find my size, to find B and L. And then after that, when I start designing for shear and moment, two-way shear and punching and one-way shear, I will have to convert to net pressure and then work my way through the design of the footing itself. Okay? Now, what is the difference here? And the design, the area of the footing is selected so that the gross pressure do not exceed the soil allowable pressure. So I would put the soil allowable pressure as my, remember this equation, stress equals load over area. I get the area up here, and this guy goes down here, and use the soil bearing capacity. So the stress is the soil bearing capacity. Then solve for the area. I found this footing area, and then after that, so this is limit state 1. Limit state 1. And then after that, I go to all other limit states. Limit states. And then to go to the other limit states, I have to convert, number 1, to net pressure. So I use net pressure instead of just the pressure. And I have to use the factored loads. Remember, this guy here is allowable stress design. Down here is LRFD. What's the difference? Allowable stress design, you just use dead and life and earthquake and wind without factoring them. LRFD, I have to use all the governing load combinations. 1.2 dead, 1.6 live, 1.4 dead, and you just figure out which one is higher. So at the time I'm done with the footing size, I have to factor the load to go to the next limit state. And we will see this in the example. Very simple, and the procedure is straightforward. Remember those equations. Those are the ones we use for the LRFD. So for limit state 2, 3, 4, and 5. over here is the flexural. How do I calculate the flexural demand and capacity of my footing? Remember, the footing is a cantilever. So I simply need to look at this here. Here's my cantilever, right? And I need to know this load. Remember, where's the critical section? Probably be here. And then where's the load? It's the load coming from this side. Pushing up this load, I have to get it to be able to calculate the moment. Where's the moment? It causes a moment that looks like this. So it is simply going to be F, this moment, will be equal to F times this distance, I call it X, times X. How do I get F? F equals the net stress underneath, ultimate, so I call it net ultimate, times the area. Which area we're talking about? To know the area, I have to look in the plan view. Here's the area. I'm looking over here. Here's my critical section. I draw the critical section in blue, right next to the column, right? And then the area where it is trying to flip it up is this area. So if I take from the distance of the critical section all the way to the end of the footing, and I name it F1, here's F1, that area will be equal to F1 times the footing dimension. Okay? Now I got the area multiplied by the Q net, all of them multiplied by X. What is X? If I found F1, then X equals F1 divided by 2. Right? Because this guy, the line of action is exactly in the middle of F1. So X equals F1 divided by 2. This is F1, which is this. And this is X, which is the distance from the center of this area to the critical section. So I go back to this equation and I look at it, I will see that the moment, the ultimate moment, equals Q ultimate times the area times the arm. Area is BF1 and the arm is F1 over 2. Okay, so Q net B F1 squared over 2. And then if I look at the other side, now the other side I'm going to do it in green, then my critical section becomes here, and then the area, I'll make it in yellow, will be this area. So everything applies to the other direction. Now if I want to see my section, now I was able to get MU, this is MU. I can get MU1 and MU2, which is in the two directions, X and Y. I want to compare this to phi mn. Which section I'm going to be looking at? I'm going to be looking at a section that looks like this. If I'm cutting here, you see this blue section? Just make it in blue. This blue section will look something like this, with some rebars here. Okay? And then this green section will look something like this, with some bars over here. Right? I have to calculate phi mn for this one. I have to calculate phi mn for this one. Exactly the same way we used to calculate things, and then compare them to MU1 and MU2. Now remember, if I ask this question, what is this width? This width will be L. Where is L? Over here. Okay? It is the distance of the width of the section along the critical section. If I ask what is this, will probably be B, right? Because this is the width of, I'm sorry, I flipped them. For the blue one, this will be B. For the green one, this will be L. Okay? So for the green one, it's L, width, and for the blue one, it's L, width. Okay? And then you just apply all the equations we had to find phi mn. You find A, C, D, C over D, or dt, and then you keep going. For the shear, we have two types of shear. One-way shear where only one side will be broken, right? One side fails. Or two-way shear, where it breaks as through punching, right? And so to understand shear, let's first talk about the one-way shear. Here's one-way shear. We need to understand what is the demand. So the demand of one-way shear comes from, here's my footing. I take a 45 degrees. That means I'm at a distance equals D. This distance here equals D, away from the column face. And then consider that this whole thing breaks off. So the load that caused this to break off is going to be the load here, right? You see this F? This F becomes my VU. Where do I get this VU from? Again, the same thing. Q net ultimate times the area. Which area? You see the hatched area here? How did I get this hatched area? I took a D away from the face of the column and then took all the area behind it. Here, I took a D away from the face of the column, and then everything after that becomes my area. Okay? Very simple. And so this one here, if I want to calculate this area, it will be my L divided by 2 minus my C1 divided by 2 minus D. All of this times B. Okay? Think about it or do it the way you like. Just take the numbers and you will see that it ends up like this. What is C? Column side. Okay? Now let's look at, now I got this VU, right? What do I compare it to? Compare to phi VC. Now it should be phi VN, but we said we very rarely place shear reinforcement in footings. So it will be just phi VC. How do I calculate phi VC? Very simple. 0.75 times 0.17 square root F prime C B times D. Okay? Now let's look at this. What is this here? This is the two-way shear. How does the two-way shear happen? The two-way shear simply happens through full punching of the footing. So it goes like this, and that guy goes up like this. Right? And then the other one on the other side goes as well. So the whole thing breaks off. Now where is the load that caused this? It will be this load. Right? So it is equal to, what is this load here? This whole load. It is equal to Q and U. This is the ultimate stress net underneath, times the area. But in this case, I want to know what's the area. Now that area is, I go here, it is this hatched area. So to calculate this hatched area, I simply have to see how far am I going away from the column. Let's think, how far am I going away? Did I go D away from the column? They said, yes, you go D away. But wait a minute, when you go D away, since it's going all around, I will average between D and 0. So I will take it D over 2 away from the column. What do you mean by this? It will be something like this. So instead of doing this, I will do this. As if I sheared it off at a D over 2. This here is D over 2. So instead of going D away, I go only D over 2 away. Okay? Why? Because I'm averaging between 0 and D. So to find this D over 2, now I got the D. To find the location of it, and it's very important, because I need to know what this surface is. You see this surface, the blue surface? The surface is very important. This is the surface that it breaks at. See, I'm drawing 4 lines. But in reality, it's a surface. What do you mean by a surface? It is this surface. If I draw it like this, here is how it breaks. Here's my column. I will resemble the punching to be like this. What is this? This is the part that went down with the column, and the remaining of the footing went up. Right? That surface is the surface of breaking. So it's very important to calculate it. How do I get this surface? I simply calculate this parameter, the blue line, which is the same as the blue line here. I calculate this blue line and then I multiply it by d. So that blue line over here is b node, the parameter. And that depth here is d. That's why in all the shear capacity calculations for punching, you will see b node times d. What is this? It's the area where you broke at. So the more you have d, the better capacity. The more you have b0, b node, the more you have capacity. How can I increase b node? I simply increase the column size. So the bigger the column size, the bigger b node will be. So that prevents punching. So let's get back to this. Now, how can I calculate b node? I simply have here C1, which is this, plus d over 2 and d over 2. I have 2 d over 2s. So it's C1 plus d. And then I have C2 plus d over 2 and d over 2. So it's C2 plus d. Now take this plus this plus this plus this. Okay, perimeter. Very simple. And then I go back and multiply it by b to get what? To get the area. Now I was able to get this area for capacity. This is here for capacity. We didn't talk about demand. Oh, demand is here. That area. What is this area? You don't get confused. This area is this hatched area. How do I calculate this hatched area? Very simple. B times L, this is this area. Minus, very good. Minus what? This nice area, C1 plus D times C2 plus D. Simple. Now I got the demand. This is called VU equals this. Where do I get the capacity from? From the next slide. Now, one-way shear, V ultimate must be less than or equal to phi Vn. We said very rarely that we have shear reinforcement in footing. Does it happen? Yes. Sometimes we do it in bridges or heavy structures, but normally we don't do it. And then the phi equals 0.75, Vc equals this. As we said, it's rare to have shear reinforcement. Going to the two-way or punching shear. To calculate B0, I calculate it like this. Twice C1 plus D plus twice C2 plus D. And then I calculate the shear capacity from these three equations. You have to multiply it by phi. Okay? Now the smallest of these equations will give me the shear capacity of punching. So in those equations we have B0, which is this guy over here. We have D, we can simply calculate D. F prime C, that's the strength of the concrete. And then other than that we have only beta C and we have alpha that we didn't know before. Now let's go down here to check what they are. Beta C is simply the ratio of the long side of the column to the short side of the column. Right? So the column is C1 by C2, simply beta C equals C1 divided by C2, where this one is the long one. Okay? And then after that I have alpha. Now we know what beta 0 is, the perimeter of the critical section. We know how to calculate it. The alpha, depending on where the column is in the footing, I have only 3 values of alpha. So if the column is exactly in the middle of the footing, here's my footing, right? Because this applies to everywhere. If I have a footing that, for example, contains several columns like this, right? They say if the column is in the middle of the footing where it breaks like this, then your alpha equals 40. If it's at the edge of the footing where it breaks like this, then your alpha equals 30. If it's at the corner of the footing that looks like this, then your alpha equals 20. So for all spread footings, central, concentric ones, your alpha will be 40. In case I have something like a raft or a combined footing where your column is at the edge of the footing, then I have to start looking, is it 30 or 20? But for the most cases, for a simply designed footing, alpha equals 40. Okay? The last limit state we have is the bearing or the load transfer between the column and the footing. What do you mean by this? It means that I want to make sure that this area here is very healthy because of the differences that comes from material above and material under. Reinforcement above and reinforcement under. We're having this neck that transfer very heavy load from the building down to the footing. So what they have here is they found this nice graph that says the split of the load between the concrete and steel. They found that in the steel portion to the concrete up on top, especially if you have different dowels, and I will explain what dowels are, will go down to be more into the concrete and less on the steel. So what do we need to check here? We need to check that the bearing is safe, bearing on concrete of the column and concrete of the footing, and that the dowels are safely taking this load. Let's now understand what the dowels are and why we need dowels. Those are the dowels. Those bars that stick up from the footing to get into the column are called the dowels, right? Those dowels are used because normally you'll have to stop your casting at the face of the footing, right? So once you stop casting, you'll have to stick some bars to get the steel cage of the column, which is this one here, and then place it, put your formwork for the column and cast the column. Okay? So now I stick out some dowels and then place my column. So this check is to make sure that the load is transferred properly. How do we do this? We calculate three different things. The dowel reinforcement capacity, which is under compression all the time, and the bearing, the concrete bearing of the footing. Now, how much the footing can take of bearing. Bearing means concrete on concrete, but they're cast at two different times. And then bearing of the column, same thing, but for the area of the column. Now, the bearing calculation goes like this. If I have something like this, it goes like this. This is going to be area 1, and that here is going to be area 2. So simply area 1 is C1 times C2, and area 2 is B1 times B times L. Okay? So now we know how to calculate those areas, and then find the area of the dowel or use an area of the dowel and do the check. Okay? It's very simple and straightforward. But if you always use F prime C's for footings and columns to be the same, and use the dowel reinforcement to be the same as longitudinal reinforcement of the column, you'll always be safe. You don't have to do this check. Now, a summary, we have the gross soil pressure must be less than the allowable bearing capacity. This is the big equation that has P over A in addition to all the loads on the ground floor or the basement. It must be less than allowable bearing capacity. The next one is checking the punching shear. My punching shear, QNU times the area. This area is the blue area. Blue area. Okay? And then calculate this, compare it to the punching capacity, which is phi VC, and this is one of the three. Remember, there's three equations. Take the smallest one of them. And then going to the one-way shear. We have to do the one-way shear twice. One to this side, one to this side. If it's a square column and square footing, then we just do it once and it applies to both sides. I calculate VU and VU. Once, again, here, I'll make it color-coded, this and this. I multiply L times F1 so the red is this. And then I multiply B times F1, so the blue is this. Okay? And then for each one, I have to check against phi VC, applicable phi VC. Remember, if it's L here, it's L here. If it's B here, it's B here. Okay?
Each one.
And then the last one is to check the bearing strength. Remember, we calculate the bearing of the column, the bearing of the footing, and we take the minimum of them in addition to the dowel strength. This gives us some load. This load needs to be less than P ultimate. Again, this is kind of reading only. You're not going to be tested on. Let's go over an example, very quick example. We have a column that is 450 square, 450 by 450 millimeters. The dead load is 1750. The life load is 1200 kilonewtons. The column is F prime C equals 35 megapascal with 8 number 29 longitudinal bars, F yield 420. And then the F prime C for the footing is 20. Grade steel is 420 as well. And it is covered with 150 millimeters fill, and then with the fill capacity, the fill density equals 19. It's also covered with a slab, 150 millimeters, so this one would be 24 because it's concrete. And then I have life load here equals 5. The allowable bearing capacity is 290 and the concrete cover is 75. Okay, going to the solution, I have to get the ultimate loads. I compare the 1.4 to the 1.2, 1.6. The 1.2, 1.6 governs. It's about 4,000 kilonewtons. Now, to find the area of the footing, I have to get the gross load, all the loads on top of it. So I have, this is the footing itself. I assumed it to be 800, right? And the fill above it, and the slab above it, and the load above it. Now everything here is unfactored. To do this, I'm going unfactored. Okay? And then what is not known is the area. I put in here the bearing capacity. This is the Q bearing capacity. Right? And then I find the area from this to be equal to 11.4. Take a square root that is equal 3.4. So I round it up. It's now 3.5 meters times 3.5 meters. Okay? This is my footing. If I check now this stress, do you think it's going to be safe? Definitely, right? Because I rounded it up. I found a smaller area. I took a bigger area, right? Now going to the next check, which would be going to the LRFD, factored loads. I have to factor the loads, which are those here, the 4,000, and then divide it by the actual area to get QNU, Q net ultimate. It is 328.5. An important question comes here. How come my bearing capacity was 290, but what I see here is 329? So the reason is because this here is a factored load, while the other one is the allowable stress of the soil is an unfactored, or should be compared to unfactored loads. D average is the depth, 800 minus 75 minus full bar. We take a full bar because that's the average between the bottom bar and the top bar. And then we calculate V ultimate, which is Q and U times the area. Which area? This hatched area. Right? And then it was 3586.4. B0 equals 4600. I substitute in all three equations. All three will have the 75% because that's the phi factor. I get all three numbers. The least is the 3600. Compare this to this and then see if it's safe or not. Now it was safe. Going to the next check, which is the one-way shear. Since it's a square footing, square column, I need to do only one side. And that one side, I get the V ultimate, again, QNU times the area, right? And then in that area, I got 900 and almost 950. Compare it to the PVC regular equation, I got 1370, okay. And then go to the flexural, same procedure, MU equals QNU times BF squared over 2. In this case, F1 and F2 are the same because it is a square footing. I get rho required. That gives me 0.0021. From this, I find area steel. And then the area steel here ended up being 5170 compared to AS minimum of a slab. Just like the slab area minimum, area steel minimum, 5040, to take the bigger number. And then find the number of bars. So just divided by number 25 bars, I get 10.2 bars. That means 11 bars. So I distribute the 11 bars in the 3.5 meters. I will get a spacing equals around 300 millimeters. I have to check this spacing against maximum spacing. What's the maximum spacing in the footing? The same like the slab. Footing is a slab. So it's the minimum of 2H and 450. And take 450 and then it is okay, so I can use 11 bars only in each direction. I check the flexural capacity using the actual area steel, and then I get A, I get C over dt to find the phi, substitute, get the actual phi mn, and then compare it to mu. Satisfied is okay. The last one is for you to check on your own. You're just getting the bearing of the footing, capacity of the bearing of the footing, the minimum of those two, and then the column bearing, this one. We take the minimum of this and this, right? And then we compare it, we'll take the difference between them and then get the area of the dowels. Or, in my opinion, it's better to just use the dowels exactly as the column reinforcement. Last thing is to sketch your footing. Now I have 11, number 25 in both directions. Those are the dowels, and that's how the sketch looks like.